Hi Laura, I'm just answering your question on getting a velocity and acceleration graph from a displacement graph. I'm going to go through example 22b. These questions are a little bit vague, and when you get a question like this in an exam, it would be far more specific. This sort of question, you need to make a couple of little assumptions. But anyway, here is the displacement graph. We know if we want to draw the velocity that we need the velocity is equal to dx dt. So that's the first derivative or the gradient of this graph. Here, the gradient is a large negative number. We don't know what it is, but the gradient of the curve there is going to be negative. And as we come down the curve, it's going to get less and less in the negative direction until we get a zero across here. When it's the derivative or gradient function is a horizontal line, the velocity will be zero and the gradient will be zero. And then from this point onwards, the gradient slowly increases as we go up the curve here to 2, 2, and the gradient is increasing all the way up the curve. So that when we go to draw the graph, we know that from 0 to t1, we've got a negative gradient that's decreasing to 0. And we know that at t1, the velocity is 0. And we go from t1 to t2, it's increasing, and beyond, the graph is still increasing. This is where you have to make a little bit of an assumption. I'm assuming that this graph, x is somewhat parabolic. I don't know what sort of parabola is or what the equation is, but I'm going to assume it's something like t squared. When I get the velocity, dx dt, it's going to be something like 2t. Okay. The important part is to know that the velocity of this sort of graph here is going to be a straight line because it's parabolic in shape. That won't be the case if it was a cubic equation. A cubic equation, when you take the first derivative, would be t squared, so it would look parabolic in shape. So I've got all this information here and I just need to put it together in the next graph. So when I know that from 0 to t1, I've got a large negative number that decreases to 0. I know it's a straight line because it's parabolic in shape. So the derivative is a straight line. It's negative, goes to 0, and then it's positive. So this graph here is a graph of the velocity. Now, if I want to do a graph of the acceleration, it's the second derivative of the displacement, or I just take the derivative of this graph here, which is the gradient. What's the gradient at this point here? It's positive, and it's that line because it's pointing. Any point on that line, the gradient of this line is going to be the same. So the acceleration is not increasing, it's not decreasing, it's staying the same. So that when I come to graph that, the acceleration stays the same, and it's just a horizontal line there. I don't know exactly what it is because this is just an example, but your acceleration graph would look like that. Part 3, when was the particle at the origin? That was just when t equals 0. It's at the origin here, your x value, and it was also at the origin at t2. Part 4, when was it at rest? That is when the velocity is equal to 0, when something is at rest. And the only time we've got a first derivative equal to 0, which is the velocity equal to 0, is at the point t1. So I hope that helps, and you can ask me further questions if you need to.